at your notes packet. Today's topic of the day is 12.2, and I have to say, all year long, I think I teach you a total of it's like 87 lessons total. And of the 87, this is quite possibly my least favorite.
Wow.
It is my least favorite because I give you close to, I think, 10 theorems today. And it is incredibly dry and incredibly boring. So, please bear with me. And if you haven't caught on to the pattern, typically when you participate, do we go a little faster? So, please participate as much as you possibly can because it'll make this a little bit more enjoyable. So, because it's such an unenjoyable lesson, I didn't give you a warm-up problem today. I thought that kind of eased the pain. In fact, I'm also deciding not to even go over the proofs of the theorems because there's so many of them. Does that kind of ease the pain? I hope so. All right, so Math Excel, you got that to take care of this weekend. We are quizzing next Thursday. At the end of the lesson, we'll take care of our check, and I have a quick color by number for you. It is only 8 problems to do today. All right, here's your advice for the day. Although homework is worth just 1 point, do it. It adds up. It really does add up. I believe in the last couple quarters, it has been about 10% of your overall grade. So without doing homework, you've just eliminated the ability to get an A. Okay? Chords. I'm hoping that this lesson strikes a chord with you today because it's all about chords. A chord is a segment whose endpoints are on a circle. Specifically in this diagram, PQ, that segment is called a chord. Notice a chord does not have to go through the center. A chord just connects endpoints of a circle. Okay? Could a chord be a diameter though? Absolutely, but is every single chord going to be a diameter? No. Okay? So let me begin the theorem madness. And it's kind of like giving you 2 theorems at once. Sorry about that. So I'm giving you the theorem and I'm giving you its converse. And because you have a theorem and its converse, this means you can write the biconditional. So my recommendation for you today with today's topics is putting the theorems into your own words. Just think about it as me giving you the facts. So let's talk about this first one. Basically what I have is within a circle, or if I have a pair of congruent circles, if you have congruent central angles, then you have congruent arcs. This makes sense because what we talked about last chapter is the fact that if I have a measure of 30 degrees here, this is a measure of 30 degrees here. And if I have a measure of 30 degrees here, then I have a measure of 30 degrees here, right? And because they have the same measure, they're congruent. Do we even really need this theorem? Not really, okay? But it kind of makes sense. But if I want to write this as a biconditional, I think of it as this way. Congruent central angles, if and only if congruent arcs. Okay? That's me kind of putting my theorem into my own words. Congruent central angles, if and only if congruent arcs. All right, let's continue talking about having congruent central angles. If I have congruent central angles, then I have congruent chords. Okay? So if I have in here, this angle is congruent to this angle, then what I know is true is this chord, AB, is congruent to, I need to use red, congruent to this chord, CD. Okay? So if I want to put this into a biconditional, because I could also say it in reverse, congruent chords means congruent central angles. So congruent central angles, if and only if, congruent chords.
Wait, ours is kind of different, I think. The converse.
So it says congruent chords have congruent central angles? Or did I just get a little overzealous?
Ours says congruent arcs have congruent blank.
I think I got a little overzealous with my copy paste from the first one, so just cross it off. Okay, just bear with me. All right, so this one, we've not really talked about the length of chords, but does it make sense that if I have this opening over here, it's impossible for me to not open up the same distance on the other side? So creating a congruent segment. Logically, does that make sense to you? Okay. All right, so I've connected congruent angles to arcs, angles to chords. What have I not connected yet? I got angles to arcs, angles to chords, What do you think the next one's going to be about? Arcs to chords. Very good, Yana. So the very last one, all three of these kind of just match up together. It talks about the fact that if I have congruent arcs, then I have congruent chords. Or if I have congruent chords, then I have congruent arcs. Okay? And ultimately it stems back down to the fact that because I have congruent central angles, I have congruent arcs. And if I have congruent arcs, then I have to have congruent chords. Okay? So if I write this as a biconditional, we have congruent chords if and only if we have congruent arcs. Okay? How do you feel about the logic of these three theorems? I'm kind of just thinking of these theorems as like properties, just facts for you to know. So that's how I'm looking at this topic as. I'm just giving you a whole lot of facts today. Okay? All right, so the first example problem we're getting into is basically kind of just like an open-ended question. So it's like, how many facts can you come up with? So this type of question would be really good as a multiple choice, to select all that apply, a true or false. Quite frankly, I will not do it as open-ended because I have 95 of you, and grading it open-ended would be just tearful. So in this diagram, what I have been given, circle O is congruent to circle P. I've also been given that segment BC is congruent to segment DF. So the question is, what can you conclude? Last year, let's see, how many did we come up with last year? Last year, we came up with more than 5 different things we could for sure conclude, and the list kind of goes on forever and ever. So let's just see what we can come up with. Let's start off with this first given fact. The circles are congruent. If the circles are congruent, what do you know is for sure true? What do you know is true if the circles are congruent? Joey?
Radius is congruent.
Very good. So we know that the radii are all congruent. So we know that BO is congruent to CO, is congruent to DP, is congruent to FP. So I could make a very long congruency statement. BO congruent to CO, congruent to DP, congruent to FP. Very good. All right, what else could you conclude because you have congruent circles? Joey already brought up the fact we have congruent radii. What else is true, Jimmy?
Congruent diameter.
We could even get into diameters being congruent. What else could you get into? This is kind of the chapter 10 portion of this question. What else do you know is true if the circles are congruent? What else has to be true? Carrie?
Could the arc measure of BC and DF be the same?
Okay, so that's coming from the second fact. You're absolutely correct. So Kerrigan's using the fact that because we know BC, that segment, which is a chord, because I have congruent chords, Kerrigan's saying we can get into arcs. Okay, so let's go into arcs. We know that arc BC is going to be congruent to arc DF. Because if we have congruent chords, then we have congruent arcs. What else is true? If we have congruent chords and congruent arcs, what else is congruent? The central angles. So we can also bring up the central angles are congruent. Let's name them. The central angle of this one is angle BOC. Central angle of this one would be angle DPF. Someone add my congruency markings in. You're at 4. What else is true, guys? Take this further. We came up with 5, like I said last year, and I know we can come up with more. Tommy?
They have the same area.
That's what I was trying to get at with before. That fact up there, the fact my circles are congruent, we know over here. We have congruent areas. What else? Olivia?
Would the triangles also be congruent?
That's what I was looking for. Very good. Olivia got it. We're looking at the triangles on the inside being congruent. Triangle BOC is congruent to triangle DPF. And I'm sorry, honey, what was the reason why you said they're congruent?
Side angle side.
Side angle side. Or, could I have said side, side, side because it was given to me that BC is congruent to DF? Absolutely. If the triangles are congruent, Aren't their parts congruent?
CCP, where
These corresponding parts.
We can use corresponding parts of congruent triangles that are congruent. So we could get into the fact that angle B is congruent to angle D, and angle C is congruent to angle F. Now let me ask you this. Could I make this a long one? Is angle B going to be congruent to angle C?
Yeah.
Why? There we go, it's isosceles. There's my 8th fact. We have isosceles triangles. So as a result, all of those little angles are congruent. So do you see why I'm so not making this an open-ended question on your quiz? Yeah, it's not going to happen. It's going to be a select all that apply, a true or false, or maybe a multiple choice question, okay? Because I could probably go on and on forever. Because could I get into some major arcs here? Could I get into area of sectors being congruent? Could I get into a lot of things? Absolutely. All right, here's your turn. And we probably kind of ruined the fun on the got it question. So on your got it question, you're just given some different information. I'm trying to get about to the same point. Like, how would you be able to get to further conclusions with different given information? Okay. Ready to look at this one and kind of chat about this one? Do you see kind of how we can go on forever and ever about all the things we can conclude? All right, so with this different given information, these are kind of the things that I'm looking for here. Because the circles are congruent, we know the radii are congruent. Because the radii are congruent, you can say the triangles are isosceles. So we know all those different things create that long congruency statement. Then you know your base angles are congruent. Okay, you guys could have also brought up the fact that therefore the triangles are congruent by angle, side. So you could have said, well, CP, CTC. Then because the central angles are congruent, the arcs are congruent. But it's kind of this like endless process of all these different things that are true. Does that make sense? My warnings to you on questions like this. Read your options carefully. I like to name things incorrectly, just to make sure you're looking for those matching corresponding parts, making sure that your angles are named properly. Do those types of little warnings make sense? All right, back to the theorems. Sorry about this. All right, so this one. The whole topic, the whole thing I'm starting off with, if you haven't caught on, is it's always within a circle or congruent circles. So, if chords are the same distance away from the center, then the chords are congruent. Okay? So in this diagram, I notice that I have E to O is the same as the distance from O to F. So what that means is my chords are the same distance away from the center. And because they're the same distance away from the center, these segments here are congruent. Those chords are congruent. Does that make sense? But what I'm looking for in the diagram is I'm looking for information to indicate that they are the same distance away from the center. Okay? That's what I'm looking for my given. So here's this example. I need to find the length of RS in the circle. It's a tough one, guys. So we got to look at given information. I noticed that these numbers right here are 9 and 9. What does that mean? If they're both 9, what does that mean? What's congruent? Very good, Yana. because the chords are the same distance away from the center, they're both 9 units away, this means that the chords are congruent. So we know that PR is congruent to SR. So in order to find the length of SR, it might be helpful for us to figure out the length of PR. So let's look at PR. What do I notice about PR? Go ahead, Susie. Very good. So one part of it is 12.5. PQ is 12.5. So is the whole thing going to be 12.5, Susie? Ah, it'd be 25, because we see those congruency markings. So PR, the length, is 25. So if PR's length is 25, what's the length of SR? There you go, 25. But this is all thanks to Jana's observation. Jana sees that they're both 9 units away from the center. If one said 9 and one said 8, could you solve the problem? No, you couldn't. We're looking for that given information in order to conclude that the chords are congruent. So now it's your turn. So you're kind of doing the flip of this theorem, the converse of this theorem. All right. You ready to check on this one? Okay, I know these are toughies. Did you get an answer of 16? Good. So because these chords are both 36, the only way that could happen is if they are the same distance away from the center. We good on that? All right, so far we've done, I think, a total of 4 theorems. 1, 2, 3, 4, and their converses. We continue. Oh, goodness. I think I have 3 more on this slide. All right, so if I have my diameter, and the diameter is perpendicular to a chord. So here is chord CD. Here is the diameter. It is perpendicular. So that's my hypothesis. So if the diameter is perpendicular to a chord, then 2 things are true. These little baby arcs right here are congruent to one another. Not only that, but these 2 little segments right here are congruent to one another. So if the diameter is perpendicular to a chord, those 2 facts are true. Okay? All right, so now let's go this way. If I have a diameter, and I notice that the diameter broke the chord up into 2 congruent parts, okay? So the diameter split the chord into 2 congruent parts. Then, what I know is true is that it is perpendicular to the chord. So I can add in the right angle marking. So these 2 theorems kind of go hand in hand. Because then if I know that this is true, then I can say, well, ta-da, my little baby arcs are congruent. You still with me? Okay. Whew. Oh, buddy. All right. So if this random segment here is perpendicular to a chord. So I have this random segment AB. I don't know who AB is, but I do know it's perpendicular to this chord. And it cut the chord into 2 congruent parts. Then that random segment isn't so random anymore. That random segment contains the center of the circle, aka making it the diameter. So these 3 facts kind of go hand in hand, okay? It's all about having a diameter being the perpendicular bisector to the chord, okay? So these are kind of all the bits and information that I'm looking for in these problems, okay? You kind of with me on this? All right, you're doing a great job today, guys. And because you're doing such a great job and because I love you so much, we're going to skip the next problem. This is not an expectation I have of you. If I am not teaching this example problem, I do not expect you to know it, okay? That's why did I even put it in your notes anymore? Exactly. So you should love on me a little bit here. It would have required constructions. Now you really like me? Okay, that's good. I see some smiles on your faces. All right, look at that. Last problem, last slide. You're doing great. All right. What is the value of each of the variables? I have two parts to my problem here. Okay. So I am solving for r. Okay. That is what I am looking for right there. And these are the observations that I am making. I am making this observation that I am perpendicular to a chord. Okay? And if I kind of extended out this line a little bit here, what would that thing be called? That's the diameter. And I'm noticing this imaginary diameter is perpendicular to a chord. And if my diameter, my imaginary one, is perpendicular to a chord, I'm fairly positive that according to the very first theorem right here, I have bisected the chord, which is really exciting because that's going to help me solve for r. Okay? So I now understand why I just learned all those theorems, because I know that this is congruent to this. If the whole chord is 14, what is the length of this tiny piece right here? So if I kind of zoom in on the triangle that we're dealing with right here. Here's my right triangle. We now know this is 7, this is 3, and this is r. What can I use to solve for r, Tommy? Pythagorean theorem. It's kind of like a big deal in this chapter, right? All right. What is my leg? What are my legs? Very good. So we have 3 squared plus 7 squared is equal to r squared. I do not believe this is a Pythagorean triple, but let's see here. 3 squared, 9. 7 squared, 49. Still equal to r squared. What's 9 plus 49? 58. So we got 58 is equal to r squared. And I'm kind of jumping for joy right now because it said round to the nearest 10th, which means do I need to simplify a radical? Woohoo! So all we gotta do is take the square root of 58. Man, I'm super pumped about that. So, square root of 58, let me see here. I didn't do it last time, so I'm gonna do it now. Square root 58, 7.615. So if I see 7.615 and I'm rounding the nearest 10th, that gets me 7.6 centimeters. Questions on how I got 7.6 centimeters? Do you understand why I was able to do that? Okay. So then we have this one here. All right, so observations. Because remember, it's all about which theorem can I use. So I'm seeing that this is 11 and this is 11. And I'm thinking, since this is the center, that dot is the center, this must be an imaginary diameter, right? All right, so I'm looking at my notes here. I'm like, okay. The diameter bisected the chord. And if the diameter bisected the chord, aha, it's perpendicular to the chord. Ah, so we're using this one right here. The diameter, that imaginary piece, bisected it. So that means it's perpendicular, which means I can add what into my diagram? A right angle. So I add in a little right angle. How am I going to solve for y? Jimmy?
I wasn't raising.
Oh, I thought you were kind of raising your hand. How can I solve for y? Isabel?
Would you draw an auxiliary from A to B and then do Pythagorean theorem?
Ah,
AB would be 15 plus that's 30.
you go, girl. I am drawing the auxiliary line. I'm adding into my diagram because AB is a radius, right? And isn't it the same all the way around the circle? And Isabel has just created for us a right triangle, so aren't we super pumped? I thought so. All right, so I'm going to draw the triangle again. So it looks like we have 11 here, y here, and 15 here. So what are we going to use? I'm super pumped about it too, Yana. All right, so we got 11 squared plus y squared equals 15 squared. All right, last I checked, is 11 still 121? All right, it's good to know. 15 squared, 225? Oof, just checking here. All right, so 225 minus 121. What's 225 minus 121? All right, and it's round to the nearest 10, so I'm kind of super pumped about it still. So y is equal to the square root of 104. And if I go to my handy-dandy calculator, I kind of feel like I'm on Blue's Clues right now. We got 10.19. So if I see 10.19, that's going to round to what? Very good. 10.2. And there was no unit of measure in this diagram, so it looks like my job is done. Do we kind of understand why I had to teach you all those theorems today, those words? Kind of annoying, but yeah, it's happening. All right, here is your guided question. It says in part B, how did Isabel's auxiliary line BA make the problem simpler to solve? It's kind of for Isabel. Is your question. Yeah, look at that, Isabel. It's because it allowed us to use the Pythagorean theorem. It's exactly what I'm looking for. All right, questions on what we learned today? Does it make sense? Okay. All right, so your final two tasks today. You have a check for understanding, which you may use your notes on, take your time on, and then when you are finished, you have a color by number activity that you picked up when you walked in the room. Great job today, guys. I know it's a topic, theorem-heavy topic, so it's kind of rough.
I haven't even finished the last one.
It's because Isabel got it for us.